Our next example has a more business orientation, and the idea here is that we have two plants that can manufacture the same item, and the challenge is to balance off the costs of each item being produced at each plant. Typically, overproducing at one plant and underproducing at another is not going to be as cost effective as splitting the production in some way between the two plants, and that's what we're going to explore in this particular problem. What we have here is costs on the manufacturing side, and we can choose to produce Q1 at plant 1 and Q2 units at plant 2, and here are the costs associated with those. The total quantity that is demanded, well, that's going to depend on the price we set. So this is going to be a fairly involved example combining the price and costs of the production. The more we produce, the total production is obviously the sum of the two productions from the plants separately. The price that we can charge is going to depend on the quantity produced, and the more we produce, notice the negative sign here, the more we produce, the less we're going to get for each item. So let's take an analysis here and first look at the cost of production, then we'll look at the profit we're going to make, or the revenue, and then the profit. The total cost of producing is simply going to be, well, the cost of producing the Q1 units at plant 1 and the cost of producing the Q2 units at plant 2, and that would be 8.5 plus 0.03 Q1 squared and 5.2 plus 0.04 Q2 squared. So those are packages there, and that gives us our manufacturing costs as a function of Q1 and Q2 together. We can simplify that a little bit. That would be 18.7 plus our fractional costs here that depend on the production. So these would be the fixed costs, and these have some essence of variable costs in them. What about the gross revenue? Well, the revenue is going to be, well, we were going to sell units, so it's the number of units sold times the price per unit. Well, the number of units sold, we said that was Q, and that's better known as Q1 plus Q2. The price per unit sold, we were told, will be 60 minus, let's get the coefficient right here, 0.04 Q. But once again, that total production can be divided into the production at each center. So we're using our total production being the sum of the individual plant productions. So here we'd have minus 0.04 in brackets Q1 plus Q2. And I think it behooves us to break this up or expand this out. We're going to have 60 Q1 plus 60 Q2 minus 0.04 times, we've got the mixed product here, so we'll have Q1 squared plus 2Q1 Q2 multiplied and plus Q2 squared. And let's leave it at that form for now. That's probably simple enough that we can work with it. So we've got our gross revenue and we have our gross cost functions. What, of course, is going to be our next step to find the profit? Well, the profit is our revenue minus our costs. Our revenue we just had a second ago was 60 Q1 plus 60 Q2 minus 0.04 Q1 squared, 2 Q1 Q2s plus Q2 squared. All of that is our revenue. And then we subtract a big term for our costs, and our costs were given to us before. They were 13.7. Here I forgot the coefficients. 0.03 and 0.04. 0.03 Q1, 0.04 Q2. Sorry, these are positives. Q2 squared. That term there being our negative costs. Okay, well, if we look down this, we can simplify this a bit further. So this is profit as a function of Q1 and Q2. The 60Q1, 60Q2, those we can't do much with. we have 0.04 q1 squared minus another 0.03 q1 squared. So here we get minus 0.07 q1 squared minus 0.08 q2 squared. We have 0.04 q2 squared minus another 0.04 q2 squared. And last but not least, we still have a 0.08 2q122. And what haven't we got? We've got that. Oh, 13.7. Fixed costs. So that fixed cost shows up as a negative term in our profit statement, which makes sense. Okay, so this gives us a lovely, rich, quadratic multivariate function, a function in Q1 and Q2. And of course, our goal is going to be to do what? To optimize our profit. So what we're going to do, we're going to use critical points to give us the values of Q1 and Q2 that maximize the profit. So that's our profit. So our first step, again, if we want to maximize this profit, is to find the critical points. And for that, we need to do the derivative with respect to Q1. So we're going to have a whole host of subscripts running around here. That's just the way it is. Derivative with respect to Q1 is 60, nothing, minus 0.14 Q1 here, minus 0.08 Q2 there, and derivative of a constant is 0. Likewise, when we take the derivative with respect to Q2, we are going to get an expression like this. When we take the derivative with respect to Q2, Q1 is a constant, so that's a multiplier. And we set them equal to 0 for the critical points. And what do we learn from that? Well, we're going to get two equations. It's not clear which way it's best to solve. In fact, I think I might just leave them as is. Again, here's where having a variety of techniques for solving equations comes in handy. I would be tempted simply to take these equations and subtract one from the other, and that'll get rid of our 60s in a hurry, which is nice. If we do that, we'll have negative 0.14 minus 0.16. That'll end up being positive. Oops, sorry, I'm mixing and matching. That's Q1, that's Q1. So negative plus the 0.08 will give us 0.06 Q1s, and negative 0.08 minus negative 0.16 is going to give us a positive value. Sorry, that's negative. Positive value of 0.08 Q2 has to equal 0. And if that's the case, then we can bring the Q1 over. 0.08 Q2 is equal to 0.06 Q1. Or if we like, we can multiply everything by 100. We'll have 8 Q2 is 6 Q1, or Q2 is 6/8 of Q1, or 3/4 of Q1. So that would be one condition, and we can then replace that into either 1 or 2, whichever we like, to find the corresponding value for Q2. Let's put it into equation 1. So 3/4 of Q1 shows up here, and oh goodness, let's use 2. I can just see the algebra working out more nicely with 2. Doesn't matter, they get the same answer either way, but 3/4 of 0.08 is going to be much nicer than 3/4 of 0.14. So into 2, change my arrow here because I changed my mind. There we go. 60 minus 0.16 Q2 minus 0.08 times 3/4 of Q1. Whoops. Q2 is equal to that. The 3/4 goes here. It really didn't matter, did it? I'm misreading my Q1s and Q2s. There you go. Good lesson in error detection. So our second equation, 60 minus something with Q2, but Q2 is 3/4 of Q1. And then we have Q1 again. What does that get us? Well, we have 60, 3/4 of 0.16 is 0.12. And we also have another negative 0.08 and that's all that. That many Q1s equals 0, and that is better known as minus 0.20. That combination means that Q1 would equal, let's bring this to the other side, we'd have 60, sorry, positive 0.20 Q1 is 60, so Q1 is going to equal 60 over 0.2, that's 60 over a fifth, or better known as 300. We found Q1, then we can combine our two features here, Q2 and the Q1 value. We're going to find Q2 at the critical point is going to be 3/4 of Q1, and that's 3/4 of 300, which I believe is 225. All of a sudden I'm doubting myself. Let's just go check there. 300 times 3/4. 225, there we go. So that's our only critical point. We'll put that on the next page. The only critical point is Q1, Q2 equals 300 and 225. Our next step is to determine if the critical point is a local max. Well, for that, of course, we need our second derivatives of our profit function. So we're going to have two derivatives with respect to Q1, two derivatives with respect to Q2. Should make this as clear as possible. And the mixed derivative Q1, Q2. So we flip back to our earlier expression for the derivatives, and then we say, what happens if we differentiate with respect to Q1? We get a nice constant. Differentiate this with respect to Q2, we get a nice constant, 0.14 and 0.16. And the mixed derivative would be, let's take the Q1 derivative and differentiate it with respect to Q2, we'll get negative 0.08. So it turns out that these are not functions of Q1, Q2, or they're constant functions of them. So we can go immediately to our D, and I'm not going to write out the formula again. We know it's the pairing of these two minus, let's put it here, the product of these two minus this quantity squared, and that would be negative 0.14, negative 0.16 times, minus negative 0.08 squared. Well, both these numbers are bigger than 0.08. We can find out the value, can't hurt, but it's going to be positive. 0.14 times 0.16 minus 0.08 squared gives you a positive 0.1016. Under those circumstances, using our rules for classifying critical points based on this discriminant value, this is positive, so this implies the same concavity in both directions, and let's just take PQ1, Q1 is negative. That implies concave down, negative concavity, concave down, and that means that our critical point by the second derivative test, is a local maximum for the profit function. And again, you see the model, I hope, here of identifying critical points and then classifying with the second derivative test. That model works smoothly once you have the function that you need to optimize defined. The process after you have that function tends to be very similar in most of these problems.